So this is physical chemistry class. Please check. I may have misplaced names and mistyped because I'm learning your names and associating. If you see someone in mask, it means that it is like a distinction decoration. It's those who are coming in person to the class. Physical chemistry describing properties of molecules by accepting the fact that electron is a wave. And in order to simplify a lot of derivations, we need computational tools, MATLAB. Today is presentations by all attendees of the class. 5 minutes per presentation. 5 minutes per presentation.
Okay. All right, so my presentation is on complex numbers, functions, the definition of arguments, and just some graphing basics. First of all, though, I wanted to talk about getting to the download path for MATLAB. So if you just take this link right here, it'll take you straight there, or you can find it by just searching NDSU MATLAB. It's important that you take this, though, because then it'll take you to this page, which links you up with NDSU, and you won't have to go through some stuff with like license or whatever. So like you'll just be applied to like the NDSU license. So then you could just click sign in to get started, and then you'll fill out some of your stuff for your new account, and then it's just this download button right here. That's pretty simple. So complex numbers, as we know, they're represented with the imaginary unit of I. So one way you can just generate it is setting x equal to integers between -5 and 0. So you get these values, which are negatives and 0. And then you could just do square root of those. And then you'll have this imaginary component put onto that, except for 0. That'll just be 0 times I, so that's just 0. So one thing that we have seen with this was for probability densities. This is one equation where we use the conjugate here. So here's an example of that where we have 2 plus 5i times 2 minus 5i. These are both conjugates. So once we multiply them both together, we get 29, which doesn't include the I component. So arguments and functions, simply put, arguments is just the defined input to the function. So here I have x from 0 to 10. So we have all the integers 0 to 10 here. And when we input them into a function, my function is y of x equals 2x squared. Then we'll be here, and it'll just square all those values of x for us. Another way of doing functions is actually making a script for it. So the good thing with this is you can actually save some of like your variables you may define as like gravity or something. So you just have to load up the script if you're working on like a new project, and then you won't have to like retype what gravity is equal to in like your command line. So here's my example of it. You just type in function for like your statement, your output equals your function name, and then your input. I just picked pizza because I was hungry when I made this. And then in the next line, you just do output equals your equation. Still I have 2x squared, so it's 2 times the input, which is here, and then you square that. So once I have this made, I can just put in, define what x is, and then just type in my function of x, and then it'll just give me the same answers as I had before. And when you graph these now, it's pretty simple. You just define what you use for x again, define y as your function, and then you just plot x and y. You can see that there are some like ridges in it though. For example, like if you did 0 to 5, you like really like shows how rigid this is. So one way when you're graphing, if you want it to be smooth, you can set x to be the line space between 0 and 5, and then your function value, and plot it that way, and it'll give you a really nice smooth curve. And that's it.
Okay.
And that's it.
Okay. Thank you. Any questions in class? Any questions online? If not, let's thank team once again. Excellent, and I really happy that you made connection to the class materials. So next is Adam.
Hello.
Okay. Camera works. Good.
All right. Here it is. All right. Can you guys see that okay? Okay. So I did a presentation on how to find derivatives and integrals using MATLAB, specifically for the derivatives using the finite differences method. So when we find derivatives, we we want to use the classical definition of the derivative as the as this limit on the screen. We want to use commands that can help us approximate and compare the first or second derivative using data that we have. It's important to note that the top portion of the new equation, so it's the like the delta sub h fx over h, it can be used to calculate the derivative, and the top portion of it can be considered kind of a difference, like a difference with respect to the function of x. So here's the example on how to differentiate. So we can use x as our variable and f as our function. We need to define our step size h, as we saw on this slide, previous slide. We want to use a low value so that our approximation is precise. So I used 0.001. So that's how you just define that h's value. But also we want to kind of generate a data set. So we set x equal to the range between -pi and pi, taking steps of pi over 32. This just gives us a whole bunch of data points and will give us a better graph in the end. Then we can set our function to the cosine of x. So this will generate another data set, basically just taking the cosine of all x values that we've generated. So here's the graph. Here's how to make the graph of our function. You see all those little data points make quite a nice graph in the end. So to actually differentiate, we can find the difference, the difference that I was talking about earlier of our in function values by diff f. But this like the definition of a derivative, we can divide by h, this difference, to get a approximated derivative value. So we can actually plot this similarly to before, this difference f over h. So here's that, and this is pretty clearly the derivative to the function that we had earlier. So an example for integration, it's kind of similar, except instead of dividing by h, we're going to be multiplying by h, much similar to dx, but we just chose to keep h for this example. Okay, so theoretically, the integral from -pi to pi for the function cosine of x should be 0. It should be nothing. So if we approximate the integral using the sum of all x values, this should be f values, the sum of all f values times h, we get a certain value. And then if we make our h smaller and do the same function, it becomes closer to 0. So this becomes a lot more precise this way. All right, questions?
Okay, let's thank Adam. Questions in class, questions online. Quick question from myself. Slide 6, can you flip back? Yes, so it goes up to 100, plus 100, minus 100, and analytically, derivative of minus cosine should be like the derivative should be in the range from plus to minus. So in this relation, once you set up your h, your increment like 0.0001, another time you set up steps between nearest positions in space like pi over 32. So would you agree that mismatch between value of h and space between nearest point would lead to the error in the absolute value?
Yeah, that makes sense.
Yep, good. Let's thank Ada once again. 5 minutes per presentation.
See me now?
Perfect.
Okay. So I had the vectors in MATLAB and then the scalar versus diadic product in Dirac's notation. Okay, so some vector basics. So you can enter in vectors a few ways. So you can simply type it out, what I did here for lowercase q, and you can just type out each number in the vector, and then you can get your vector. And then you can also, for uppercase q, what I did here is you can define your vector by the starting value, its ending value, and the interval that you want to, each interval in between. So I just made the same vector, just using a different format, starting at 1, ending at 4, an interval of 1. You can also, on the right side for R, you can see you can also do vector matrices in, you can do 2 by 2, 3 by 3. You can make these as large as you want doing this notation. And then you can reverse the rows and columns by just doing the apostrophe after your vector, or q prime. So you can multiply these vector matrices by each other, but to do so you have to have the same number of rows in the first matrix as the same number of columns in the second. So in here, q prime has 4 rows, lowercase q has 4 columns. Therefore, you can multiply, and then you'll result in this matrix right here. And then if they aren't matching, you will get an error, and then it's the incorrect dimensions for matrix multiplication, and then it'll suggest that you correct and make sure that the rows equal the columns in the matrices. And then this multiplication works the same for division. So the diadic for scalar product, the diadic product is what you saw in the previous slide. It's just essentially when you multiply the vector matrices, you'll get another matrix or operator for a product. And then the scalar, which equates to the dot product for the vectors, when the row, the first one is minimized, so 1 row, and then q prime has 1 column, it's going to produce 1 answer. So it's going to produce a dot product for the vectors, and that's the scalar product. So for Dirac notation, for the first one you have bra, which is it represents a row vector, so lowercase q on the right side. 1, 2, 3 would be the bra, the less than x straight bar, and then the bar x less than x ket. It represents a column vector, so it'd be the uppercase q prime right here. That'd be represented by the ket, or the notation here. So yeah, when they're multiplied, bra versus kit, you're going to result in the scalar or dot product. So you're going to get the single answer for your multiplication. And then if you do multiply ket times bra, you're going to result in the dyadic product, which will result in that matrix that we saw in the previous slides. So bra mathematically represents a vector in an abstract vector space, while physically it represents a state of a quantum system. And then ket mathematically represents a linear functional, which could go deeper into that, but that's not really what the presentation's about. And then we have Dirac notation, continued. It's commonly used in quantum mechanics since a lot of wave functions and other things can be described using vectors and this notation. It can describe wave functions, quantum superposition, and then just a few examples of calculations that utilize the Dirac notation. Spinless position wave functions and then overlap of states are just a few, but it has a lot of applications across quantum mechanics. And that's it.
Okay, please join me in thanking Connor. Sure. Yeah. Any questions in class? Any questions online? It was crystal clear. Let's thank Connor once again. And next in our schedule is Spencer. Spencer, please start sharing your screen. And yeah, thank you for enabling camera. Now we do not see it again. Can you please re-enable camera?
Can you all see me and see the slide? Okay.
Okay, yes, we do see you. Please go ahead.
All right, so we're going to be talking about matrices in MATLAB and kind of everything that you can do with them, so that way we can figure out how to make MATLAB work for us, so that way we don't need to go through the headache of the linear algebra process. And so we're going to be talking about transposing the matrix, the determinant matrix, matrix multiplications, how to take the inverse of the matrix, and visualizing a matrix within MATLAB. So for those of you who don't know, transposing a matrix is an operator which flips the matrix over its diagonal. So you can see down here kind of you take the 1 and 4 and you flip it on its diagonal to give you the matrix transposition. And it's written as A superscript T. Here is an example in MATLAB. So the first step is you need to define what your matrix is. So in this example, it's A is equal to 1, 2, 3, 4, 5, 6. And then the term that you write, or the calculation I should say, is the transpose parentheses A. So you'd say B is equal to transpose A, and then you'd get this as your final answer for the transposition. For the determinant matrix, it's written as vertical bar A, vertical bar, and it's the same notation as the absolute value. An important note here is in order to have the determinant of the matrix, it needs to be square. So like 2 rows by 2 rows, 2 rows by 2 columns, 3 rows by 3 columns, etc. So again, over here, we have an example. So we have to first define C. So C is equal to 3, 8, 4, 6 in that matrix, and a standard 2 by 2 matrix. And the shorthand for the determinant of the matrix is the det of C. So make sure that you define D and the determinant of C. So again, here is the calculation on MATLAB itself. Matrix multiplication. This is where you multiply a matrix with another number or another matrix. We kind of went over this in the last presentation a little bit. However, it's easy to do in MATLAB as well. So you need to first define your first 2 matrices. So in this case, I've defined A as 1, 2, 3, 4, defined B as 4, 5, 6, 7, and then it's time to be multiplied. So it's the syntax is literally A star B, and that gives you your answer for the matrix. Sometimes, if your columns if you don't have enough rows equal to the amount of columns, you need to do it reversed. For the inverse matrix, it's the reciprocal of the matrix. And again, the matrix does need to be a square. So 2 by 2, 3 by 3. And you'd write this A superscript minus 1, not 1 over A, because you can't really divide by a matrix. For the syntax, you have to first define your matrix, 6, 7, 9, 10. And then it's the inverse function. So you define B as the INV of parentheses A, and that give your answer. So again, here is the example from MATLAB. You can see how this yields our inverse matrix from our function. Visualizing the matrix. Now, this is the last part of kind of this PowerPoint, and this is about, you know, seeing your matrix from a different perspective. So first things first is you would define S, or A in this case. So S is equal to this long stream of numbers. And then you'd use the command ImageSec. So IMAGESC, and then parentheses your variable. So again, you can see here my variable is A, which again yields this matrix down here. ImageSec parentheses A yields this matrix over here, and that'll appear as a kind of a figure above your kind of workspace in MATLAB. And that's it. Anybody have any questions?
Okay, let's think. Answer. So what is the color code? In your last slide, there were yellowish, greenish, bluish. How does it go with ascending, descending of rainbow?
From how I understand, it is ascending.
Okay.
Yep, so.
More questions in class, online? In which circumstances you may need exponential of a matrix?
What'd you say? I missed that, I'm sorry.
Exponential of a matrix. It is not part of your presentation, but one can take exponential of a matrix, and just a question, do you think we will ever need it?
Most likely, taking the exponential of a matrix is a good handy tool to have in your back pocket.
Okay, equal for evolution operator. Okay. Okay, please join me in thanking Spencer once again. And let's check. Someone is on the chat. Oh, okay. Yeah, it was Spencer. So the next presentation is by Jared, who is here in class. I see audience encourages him. Yes. Oh, I need to start sharing. I always forget it, so that everyone who is offline does see his presentation. Share. Okay. Start setting and focusing on the structure. Okay, floor is yours.
All right. So I'll be talking about the eigenvalues and eigenvectors in MATLAB. So first is how to calculate the eigenvalues. So if you put in a matrix on MATLAB, so I just had MATLAB come up with just a random matrix, and I set that equal to J, as seen on the left. And then you can type in EIG, and then your variable, in this case it'd be J for my matrix. You hit enter, and it'll give you your eigenvalues. And if you want to change the format of your eigenvalues, you can put in a comma, a matrix, and it'll put it into a diagonal matrix. There's 3 values. And putting it into the diagonal matrix could be useful for when you multiply it by other matrices. So this slide, we can also see that MATLAB can handle complex numbers. So if you have negative values in your matrix and you want the eigenvalues, it'll give you a real number along with a complex number. And again, in V, we can just see that I put it in a diagonal matrix. So if you put in the command bracket V comma E for any 2 variables you want, and I pick V and E, and your eigenvalue of your vector, say if you're, or your, not vector, but of your matrix A, you'll get 2 different sets of values that'll come out. So the first in V will show you your eigenvectors, and then E will be your eigenvalues in that diagonal matrix form. So then what is the eigenvalue and eigenvectors calculating? So take a look at the top left. You have a matrix times by a vector, equals the eigenvalues times by another vector. So this is the equation of what an eigenvector is. So then you can do some mathematical operations and then take your eigenvector, which I use just the variable epsilon to represent it, and multiply it by identity matrix, and you'll just get E in the A slot and B slot. And then you can multiply those two together to get A minus epsilon B C D minus epsilon times by your vector yet. And then you can take the determinant of that, which will give you up on the top right A minus E times D minus, or A minus epsilon D minus epsilon minus BC, which will give you a form of A squared plus dx plus c. And then you can use the quadratic formula, and then those values will be your eigenvalues. And you can plug your eigenvalues back into your equation to find your eigenvectors, which would be x1 and x2. And then, so you end up with, in this case, a 2x2 matrix, 2 eigenvalues and 4 eigenvectors. And that is it.
Okay, please join me in thanking Jared. I'm keeping social distancing, but there are some questions. Please stay here. Any questions in class? Any questions online? I do have a couple, too.
Okay.
So can you flip back? Yeah, here. Which of those data elements will serve as eigenvectors? Columns or rows?
The columns. So,
how to check that it is correct?
you can take your column, set that as a vector, and then multiply that by your original matrix, and it should give you the eigenvalues.
Multiplied by the same eigenvector.
Yes.
Super, super. I'm very happy. And question number 2, in relation to physical chemistry class, for which matrices you expect we need to find eigenvalues and eigenvectors? For which operators?
Probably the Hamiltonians.
Super. Both questions absolutely correct. I thank Jared once again. 5 minutes per presentation.
You want me to do mine now?
Yeah.
Okay.
Yeah. And please share the screen.
Okay.
Okay.
Do you see it? Okay. How do I do it as a slideshow? Oh, there, maybe. Okay, so I did plots, 2-dimensional plots and 3-dimensional plots. So the 2-dimensional plot, you need to use the plot function in order to create that. So you can see here in my example, I have an x value with the function, a y value, and then you have to put plot x of y, and then your graph automatically pops up. And to add labels to this, you just add on x label, and then you label whatever you want as your x label. And then you do the y label, and then you title that, and then the title, and then you put whatever your title is. So there I have that. And then you can also plot a dashed line. And when you do this, you just do this last function here on the bottom, which is plot x, y, and then the apostrophe r dash dash r, or apostrophe again. And then there you get that plot. And then when you do this, you can see that the labels all disappeared, and MATLAB automatically does that every time you call a plot function. So then if you want to combine the two together, you have to use a hold on function. So as you can see, I have the x and y, and then the plot x, y, and then I put hold on, and then you do your other one, the y2 cosine, and then continue. And then you have to put hold off after that, and then you'll get your plot here. And then there, I'm just combining both of the graphs. And then to do 3-dimensional plots, you have to use both the surface function and the mesh function to display surfaces in 3 dimensions. So here you can see I have mesh grid, and then the last line is the surf function. So the surf function displays both the connecting lines and the faces of the surface in color. And then the mesh function produces surfaces that color only the lines connecting the defining points. And then you can also do subplots. So you can display multiple plots in different subregions of the same window by using the subplot function. So here you can see I have 4 subplot functions. And then, so the first 2 inputs of the subplot indicate the number of plots in each row and column. And then the third input specifies which plot is active. So the example shown here, I've created 4 plots in a 2x2 grid within the figure window. And that's what you get.
Okay, please join me in thanking Kennedi, and 5 minutes per presentation.
All right, can you hear me?
Yes, but now you need to and start sharing once again.
Yeah.
We do hear you.
All right.
Yeah. Okay, everything is perfect.
Okay. All right, so I did my presentation on some basic scripting and some basic sort of tool set ideas in MATLAB. So we'll talk about basic MATLAB file modification and execution first. So this is basically how to create a notebook, save a notebook, load a notebook, and execute notebook code. So in creating a notebook, it's fairly easy. Simply go to the top left, click on New. It will pull out a drop-down menu of all the different types of notebooks you can create. So you could do a scripting notebook, a live script notebook, a function-based notebook, a live function-based notebook, and there's a couple other options there, but those are less important for what we do here in PChem. And then for saving a notebook, whenever you're in a script/notebook, simply it's in the top left. All you do is click save, and you can do it as save as, or you could do it as an export if you do the drop-down menu. For instance, you can export as a PDF or a Word document, and this will show your code as well as any diagrams that you have within that script or notebook. And that is how you save that. For loading notebooks and scripts, simply you can either do open or import data. The difference between the two is that importing data already takes your currently open file and imports data from the file that you open. So essentially it's a lot like opening a regular file, but instead you're just copy pasting the data from one file to another. Whereas with just the regular open function, all you're doing is just opening one of your notebooks that you already have saved, and you can find it in any of your computer drives, because all it does is it just takes you right to your file system. So, and then we'll just talk about some basic scripts. So if/then scripts, or for and while loops. Basically, these are just some coding language, basic coding language, syntax, and some tricks for repetition and conditional execution of statements. So for conditional statements, which is like if-then statements, we have if, which is just when a condition is set, the subscript under it will run. So in this case, we have like the condition for my code is when your number is less than 0, it will display negative. So all this is doing is this is detecting if the number that you entered into the input line is positive, negative, or 0. So in order to find the positive part of it, we need to add another part of this, which is called else if, which is just an extra condition that'll run a different subscript, which is very similar to if, It's just an additional to if. So all it'll do is just it'll run a different script. So in this script, the else if is your number is greater than 0, which just means that it's positive. So it'll display positive on the output line. And then else is when none of the conditions or the preset conditions by if or else if are met, then just run a different subscript, which in this case is just display 0. So since 0 is not positive or negative, then that else statement will just simply display 0. So now let's talk about for and while loops. In this case, I have sort of a nested for loop as my for loop script, which I just used to find primes for numbers 2 through 100. And then the while loop is simply doing repeated addition and displaying those values. So a for loop essentially for some input, it will do what's defined for the loop until a break condition is met or until the input runs out of value range. So in this case, we have like for I is equal to 2 colon 100. So what that means is that it's gradually counting up from 2 to 100. And if it reaches 100, it'll break. But as you can see, there's a break in the code. So we have break, semicolon, if factor found, not prime. So what that means is that if there's a factor found within that mod I-j, then that means that it's not going to be prime. And then it'll break the for loop on one of them, and then it will fprint, and then go back to the original for loop, and it'll keep looping. So that's what like a nested for loop kind of does, where one for loop is inside another, and if a condition is broken, then it'll go to the other for loop. That's sort of the deal with that. And then for a while loop, given some condition, the statement will loop until a break or until the condition is met. So in this case, we have while a is less than 100, fprint values of a is equal to a plus 5. So this is just repeated multiplication where a is initially equal to 1. So we keep adding 5. So 1, 6, 11, 16, all the way up until 96, which at that point, it's less than 100. So, but once we go past that point, then it'll reach 101, which is greater than 100. So that while loop will immediately stop at that point, and then we'll be done with that while loop. All right.
Well, many thanks to August to this important presentation, which helped all of us to develop a mindset of professional programmers, and we all with time have chances to become gurus of programming. And the specific question for your for loop, please share your intuition and vision in which circumstances we may need for loop in relation to physical chemistry class. Like here you were going through just natural numbers and checking if they're prime. What would be the objects to count and go over in the class?
So typically for loops are very good at using a subset, a very large subset of numbers and sort of breaking them down for code. So my guess would be for numerical, solutions to differential equations would be one of them, finding certain values of functions that may take a lot of computational power. So things that take a lot of computational power, for loops are typically good for sort of compacting them, essentially. While loops can sometimes be a little bit better at that. It really depends on if the conditions are like statement based, or if it's just checking through a bunch of numbers. For loops are a little less, how do I say, robust than while loops, but they are a good way of brute forcing certain things. And we often do numerical integration in PChem, as well as you know, estimations of functions and such. So using a for loop to find solutions, as well as using for loops to essentially do the manual labor for us during labor-intensive jobs, makes it a lot easier on us as programmers for any sort of PChem software that we're using.
Super, thank you. So if we are interested in wave function, which depends on position and time, which of those arguments Zane is going to scan through by for loop in the next presentation?
I would say that if we're looking at certain, conditional statements, I would say a while loop would probably be a little bit more robust with wave functions.
Okay, and would you guess he would scan position or time in the loop in the next presentation?
I would guess time.
Yeah, good answer. 5 minutes per presentation. So next 5 minutes you are the instructor.
Awesome. Well, we're going to go over movings, saving data, and loading data. And I know August touched on saving and loading, but I learned a little differently. So for loading data, I usually use the syntax. It's just load, parentheses, file name. And then you can use different formats, as in ACSII, which is a Word format. And then, or you can do it in a mat format, which is read by MATLAB, And then saving data, same thing, just save, parentheses, file name. And then you can only save different or some variables in your project that you're making. And that's just comma variables. And then you can format it by just adding your format at the end. Writing a video is a little bit more tricky. So when you write a video file, you have to pretty much write a script, like August said, loop the script, and then animate it by getting frames from the script. So here our equation is II equals the square root of -1. And then down here, it's e to the exponent of II times x minus t. And that's the equation that we're going to be animating in the movie. So when our current frame is our get frame is just a screenshot. Looping it's just a for script like August mentioned. And you just loop it as many times as you want, and then this is the amount of time each frame is on the screen. And yeah, this is how that's the name of your file. And then, yeah, that's pretty much the way it goes. And then this is how you save it. This was a little bit tricky in my mind. So ls is just the name of it, where you can find it. PW is where it's saved. And then if you run it again, it renames it as movie temp, or mine was movie template.m. And then if you run it and then see where it is again, it'll be a .avi. And then it's shown where it's saved. And then this is the, I don't know how to play it, but it should play and it does a little corkscrew fashion.
And just
oh, there she is. And that is the function that was animated. Right?
Okay, yeah. Questions from the audience? Questions from online? Of course, yeah. Online? No one? Next time you should start giving big credit for each question. What would you do, or how would you plan your activity if you anticipate that your movie may not work? If you like make a job interview, you want to show a movie and it doesn't want to play, how would you?
You can save it to YouTube like we did, and then just go to YouTube. And play.
Right, and just click paste here.
Yeah.
Yep, that's good. I'm happy.
Awesome.
No questions? But thanks, Zane, once again. Completion of the meeting. So let me thank all presenters and all visitors. Next presentations will be in about a month from now, and everyone who presented accumulates substantial credit towards final grade. So with this, let me